Have you ever wondered how professionals make predictions about likely outcomes for an upcoming election? Well, they go through something known as population sampling. And today, we're going to introduce that notion of population sampling, looking at how we can make our own predictions. So, let's begin. Now, throughout this topic, there's going to be some new words for us to get to know. The first of which is population. When I talk about the population in statistics, I'm talking about everything that we're analysing as a whole. Now, let's put that into perspective. Let's pretend for a moment that I'm collecting some data to make a prediction for an upcoming election. The population in this data would be every single person that's eligible to vote. Now, when I'm collecting that data, I've got two options. I could take a census. Now, a census would mean that I would poll every single person that's eligible to vote. So it would mean that I'm collecting data from the entire population. Now, as you can imagine, collecting data from an entire population could be both time-consuming and expensive. So often we don't actually collect data from the entire population. Instead, we collect a sample of that population, which is to say that we collect information from some of the population instead of the entire population. Now, why do we do this? Well, we do it to make predictions about what the entire population is likely to say. Now, when we're taking a sample of a population, there's two ways that we can do it. We can do it in a completely random fashion, or take a random sample, where every single person in that population has an equal chance of being selected. Or we can use a non-random sample, which means that we're using some kind of criteria to select who we're collecting the data from. So with that in mind, let's have a look at a problem that involves coloured buttons. So here I have a bag filled with 1,000 buttons, all of them the same size. The buttons are purple, red and blue. A sample of 50 buttons is taken and it's found that 23 are purple, 17 are red and the rest are blue. Now, the first thing that we can do with these statistics is write the proportion of purple, red and blue buttons out as fractions. So to find the proportion of purple buttons, we need to look at how many purple buttons we had in our sample, which is 23, and we put that out of how many buttons were in our sample, which is 50. And now we've represented the proportion of purple buttons as a fraction. For red buttons, we do the same. We have a look at how many buttons did we have that were red in our sample, which was 17, and we put that over the total number of buttons in our sample, which was 50. Finally, we do the same thing with our blue buttons. We look at how many of our sample were blue. In this case, we need to add together the 23 and the 17 that weren't blue, which is 40. There were 50 in our sample, so that means 10 of them must have been blue out of the 50. Now this can be simplified to be 1 out of 5. Now we've worked out the proportion within our sample that was purple, red or blue, we can use this information to make a prediction about the whole population. In this case, it's asked us to predict how many blue buttons might be in this bag. Now, in order to make an estimate using the sample that we've collected, it's equal to the proportion multiplied by the total population of which we got our sample from. Now, in our problem, the proportion of blue buttons was 1 over 5. And the total population that we got the sample from was 1,000. Now, when we multiply these two together, we find that our estimate is 200 buttons within this population are likely to be blue. Now, when we make this sort of prediction using only a smaller sample size, there is likely to be a margin of error. And they've found that that margin of error is usually plus or minus 5%. So what that means is, if we subtract 5% from our 200 buttons and add on 5% to our 200 buttons, we'll create this range that the total number of blue buttons is likely to be within. So, the range is equal to the estimate that we just calculated plus or minus 5%. So what that means is we need to work out what 5% of our estimate of 200 is. So that is equal to 0.05 multiplied by 200, which is equal to 10. Now, our range is equal to 200, because that's our estimate, plus or minus this 10. So therefore, our range is going to be between 200 subtract 10, which is 190, to 200 add 10, which is 210. So in a sample of just 50 buttons, I've now found a minimum and a maximum range that the total number of blue buttons is likely to be in the full 1,000 or the whole population. So what we've learned here is if we collect a sample of the whole population, we can use that sample to find an estimate of how many there might be and a range to that estimate of where it's likely to fall. To do that, we first need to find the proportion of our sample. Okay, so let's take a closer look at how we collect samples and what is known as the sample bias. Now, how you collect data can be very important. You've got to make sure that you're not getting a bias within your data. For example, if I wanted to know how many people in the world liked fish, and I went to a fish store and only surveyed those people buying fish, there's likely to be a bias in my data towards people liking fish. So I want you to pause the video here for the moment and have a look at these three situations and think to yourself, is the data likely to be biased or not? But also, why? Okay, so have you thought about it? Excellent. Let's start with A. You want to know people's favourite foods. So you ask people coming out of McDonald's. Now, if you're interviewing people that are coming out of a specific restaurant or fast food chain, there is likely to be a bias towards a certain type of food. So therefore, our situation A is biased. Now in B, you want to find out whether residents want a new shopping centre built. So you pick every fourth person on the electoral roll. Now the electoral roll is generally organised in just alphabetical order. So if you pick every fourth person, you're getting a pretty random sample. So that sample is likely to be fair. Now part C is a bit of a tricky one. You want to find out what residents think of the new proposed pool. So you email all homeowners in the area. Now at first you seem to be getting the opinion of everyone in the area, so you might think it's fair. However, I'll throw a couple of things at you. For this to be fair, everyone first must have access to their emails and must respond. Now this isn't always true. So already you might not be getting the opinion of everyone, but only those people that regularly check and respond to emails. The second thing though is, what about those people that own a home in the area but rent it out? You're not actually getting the opinion of those people that rent within that area. You're only getting people that own homes in that area, and those people might live in a totally different area from that property. So if you're collecting the opinion from those people, you might be getting a biased opinion because it doesn't actually affect them. So C is in fact a biased method of collecting data. So let's reinforce what makes fair and reliable data. Fair and reliable data must be collected from a completely random selection within the whole population. The second that you're selecting people off of some sort of method that might create a bias, it is no longer fair and reliable data. Okay, so I want you to have a go at some practice questions at home. Question 1 and 2 are very similar to what we've discussed in this video. Question 3, on the other hand, is designed to challenge you a little bit. We've got a coin here that we've flipped 100 times and then we've collected some data. Flipped it again 100 times and collected some data. We're trying to work out whether this coin is completely fair or whether there is a bias to this coin of landing on heads more than it lands on tails. Can you work it out?